Hello, Professor. My name is Chao Zichun. My metric number is 232039194. It's my great honor to introduce my research. The title is Machine Learning-Based Diabetes Prediction Model Construction and Analysis, a case study of the Kaggle Diabetes Dataset. This study aims to address the global diabetes challenge through a data-driven approach. The background of this study is that diabetes has currently become a key public health problem. Meanwhile, the medical expenditure on diabetes treatment is expected to reach $1 trillion by 2045, from $232 billion in 2007. However, traditional prediction methods based on a single biomarker, such as fasting blood glucose, cannot capture complex risk factors, resulting in limited accuracy. This gap moves us to explore machine learning, which can integrate multidimensional data to enhance the reliability of predictions. My research focuses on three key goals. The first one is model construction, developing powerful prediction models using algorithms such as random forest and XGBoost. The second one is the key solution, solve the problem of data imbalance through SMOOT, and enhance the feature correlation through Pearson correlation and variance inflation factor analysis. The third one is clinical value, using the sharp value to enhance the interpretability of the model and achieve practical application in a mobile medical environment. The data source of this study is the Kaggle Indian Diabetes Dataset, which contains 768 female records with 8 clinical characteristics such as blood glucose, BMI, age, and a binary objective, diabetes status. First, pre-processing performs median interpolation and outlier truncation on the missing values of the source data. It can be seen that these two tables compare the counts, means, standard deviations, minimum values, and maximum values of each feature before and after data cleaning. After cleaning, the feature distribution is more reasonable, improving the data quality of subsequent analysis. Subsequently, by using feature engineering, 3 interaction features were constructed, namely glucose over age ratio, BMI multiplied by diabetes pedigree function, and blood pressure multiplied by insulin. This study compared 7 algorithms: logistic regression, decision tree, random forest, KNN, naive Bayes, XGBoost. The random forest model combined with smooth oversampling was optimized to solve the problem of class imbalance. Meanwhile, the sharp method is introduced to evaluate the importance of features and explain the decision-making logic of the model. Model performance results. After model comparison and smooth processing, the F1 score of the random forest increased to 0.655, and the AUC rose to 0.834, both of which were superior to other models. In terms of feature importance, blood glucose, BMI, and age became the most influential predictors, consistent with medical knowledge. The interaction feature, blood pressure-insulin interaction, also shows significant contributions. As shown in the sharp characteristic interaction grid diagram on the right, the cross interaction between glucose and BMI, as well as between glucose and age, highlight their synergistic effects on the risk of diabetes. The visualization results all support clinical interpretation and gut target screening for high-risk groups, such as individuals with elevated blood glucose and BMI. As can be seen from the figure, the F1 score is maximized at 0.34, set a high sensitivity threshold of 0.36 for large-scale screening. The innovation points of this research are as follows. 1. Feature engineering of medical logic and data-driven. 2. The smooth oversampling technique is adopted to handle the problem of data class imbalance and improve the prediction performance of the model in the scenario of imbalanced data. 3. Achieve interpretable AI through SHARP to enhance the trust of clinicians. This research has multiple commercial application values. For instance, for pharmaceutical companies, precise screening of clinical trial participants may shorten the research and development cycle by 12 to 18 months. And medical corporation, health management software for personalized screening can be developed. The impact on health insurance companies is based on risk stratified pricing. The claim settlement rate is reduced by 13% through intervention. Limitations of this study. 1. Database, lack of male or multi-ethnic samples and lifestyle data. 2. The model has insufficient interpretability and doesn't involve the prediction of diabetic complications. The following research directions can be considered in the future. 1. Expand the dataset with multi-ethnic and continuous blood glucose monitoring data. 2. Integrating convolution neural network and long short-term memory for time series analysis. 3. Develop a visual dashboard for the electronic medical record system. Conclusion. In conclusion, our random forest mode SHARP model demonstrated excellent performance in diabetes prediction with an F1 score of 0.655 and an AUC-ROC of 0.834. This model verified the clinical correlation of features such as blood glucose and BMI, provided interpretable decision thresholds, and paved the way for lightweight mobile applications. We believe that this research has contributed to the early screening of diabetes and precision medicine. Okay, that's all. Thank you for your listening.